Hiya, so we're going to go through question 1 of this 24 question extravaganza. I'm going to give you hints, tips and tricks on how to approach questions and the things that they're going to ask, as well as, of course, go through some theory. Another thing that's going to be useful for this is looking at different parts of the topic. So this question here is specifically a particle physics question. And it's from an AS paper, okay? But it does have some interesting things here. So we've got the word describe the interaction. So this is the interaction that is responsible for keeping protons and neutrons together in a stable nucleus. You should include details of the properties of the interaction in your answer. So this question is 3 marks, so I need to say 3 things here. Okay, so one of the things that's important, so we've got here a mark scheme there, okay, is there's normally with mark schemes, especially for written questions, there's lots of information, especially when they want you to have information. But I'm going to talk about the key terms in here and how to disseminate a mark scheme. So describe means you have to give details, etc., about the situation. And there's key terms they're using here. They're saying interaction. So for a particle physics question, talking about interaction means things like the strong, the weak, or the electromagnetic, okay? So if you're dealing with protons and neutrons, you're dealing with hadrons and only hadrons. Therefore, describe the interaction that's responsible for keeping protons and neutrons together stable in a stable nucleus. This is the interaction is known as the strong interaction, okay? Because it's only to deal with hadrons. We're not dealing with leptons or mesons. We're not dealing with leptons, sorry, we can be dealing with mesons, but we are dealing with just hadrons here, okay? You should include details about the properties of your interaction. So the strong interaction is the name of the interaction, okay? And the strong interaction is actually all to do with the strong force, okay? So the strong interaction, of course, is attractive from 0.5 to 3 femtometers in distance. And it is repulsive from 0 to 0.5 femtometers, okay? Now, if you go to the mark scheme on here, so if I just grab a mark scheme here, you can actually, there's loads of marks that you can get here. So for example, you mentioned the strong interaction has a short range or mention less than, so it has a short range or mention less than 5 femtometers. It's attraction up to 5 femtometers. Repulsive, any distance below 1 femtometer is 0 and negligible. 1 femtometer only affects hadrons, baryons, mesons, mediated by gluons and pions. So you can actually have mentioned quite a lot. So I could have actually gone into a lot more detail here. I could have said, it said, describe the interaction that's responsible for keeping protons and neutrons together. The interaction is strong interaction, and I could have mentioned because only hadrons are involved. Could have mentioned that. That's an extra bit I could have mentioned. But I'm talking because it's keeping together. When you mention the word strong interaction and they're talking about keeping nucleus together, you need to talk about what it is. So mentioning it's attracted from 0.5 femtometers to 3 femtometers in distance. So they said anything, if you look at the mark scheme, anything less than 5 femtometers, okay? So 0.5 to 3 femtometers, and it's repulsive from 0 to 0.5 femtometers. So that actually would have got me, if I had mentioned because only hadrons were involved, these are worth 3 marks. But of course, you could have mentioned what the strong interactions exchange particle was. It is a pion, okay, or a gluon, and things like that. So this is one of those really weird questions, but it's a couple of tips for this one. Describe means you're not explaining why that thing exists. You are just describing physical properties about the situation. The fact that it's mentioned interaction twice implies it's one of the 3 interactions for that. So strong, weak, or electromagnetic. It was one of those 3. And it's talking about protons and neutrons. So they have very specifically identified hadrons here. So which ones are involved with hadrons? So it's the strong interaction there. Okay. So nuclei can be decayed by alpha and beta decay. In alpha decay, only 1 particle is emitted, but in beta decay, there are 2. Explain how baryon number is conserved in alpha and beta decay. So in alpha decay, in alpha decay, I should be writing in red, sorry. So this again is a 3-mark question. So they're asking how baryon number is conserved in alpha and beta decay. So in alpha decay, so that's going from, so in alpha decay, that is going from an element, so I'm going to call this element X, with an atomic number and a proton number, goes to element Y with 4 less atomic number and 2 less proton number, plus an alpha particle at 4-2 plus some energy. Okay, so alpha decay, that's what's happening here, and it is the process where protons, 2 protons and 2 neutrons are ejected from atom. There is no conversion, so therefore the baryon number is conserved. So what's actually saying here is that this process where 2 protons are ejected from an atom. Okay, so they're ejected from the nucleus of element X, they come element Y, and so there's no conversion of elements. It is just a straightforward that they're just ejected from the situation, therefore baryon number is conserved. In beta decay, you have got a neutron being converted into a proton, plus an electron, plus an anti-electron neutrino. Since a neutron is converting to a proton, which is another baryon, the baryon number is conserved. The beta minus and the anti-electron are leptons. Okay, so having a look at the mark scheme for this one here. So in alpha decay, so if I just grab this up here, zoom in a little bit more, it says in alpha decay, the number of protons neutrons is unchanged, or the parent nucleus equals the total number of the nucleus and the alpha particle. In the beta part, the neutron changes into a proton. Beta I have a 0 baryon number and a 0 there. Only refers to the baryon number and the nuclear number. Second mark point will be shown in the equation. Okay, can be shown by equations. There's loads of little other marks here. Only refer to baryon nuclear number of the alpha particle, then do not award first mark. Beta particle neutron have 0 baryon number here. So have a look at my answers here. You see that I've mentioned this process where 2 protons are ejected. There is no conversion, therefore the baryon number is conserved. That will give me a mark. Because I've mentioned if we look at the mark scheme here, that the alpha decay, the negative are unchanged, or the baryon nucleus, the total number of baryons in this long thing here. And so I'm saying here in beta decay, a neutron changes into a proton. So beta decay, since a neutron is converted to a proton, which is an error, the baryon number is conserved. It goes and the beta they are leptons. So I've mentioned the fact that, of course, they would have no baryon number at all. Okay. So kaons and mesons can be produced by the strong interaction between pions and protons. So this is actually a key term here, this strong interaction, okay? The equation shows below that the lambda particle, this lambda 0, is produced to deduce the quark structure. So the strong interaction is where strangeness is conserved. And as you can see here, I've got, I can't spell conserved today. This is a kaon, it has a strange quark, okay? So one of these things with here is what I tend to do is I write the formula out. So I've got pi on naught plus pi plus goes to a k on naught plus this sigma naught. So charge-wise, I've got -1 plus 1, so the charge is conserved. The baryon number, I've got 0, I've got a +1. This is 0, so this means my thing must be a baryon. There aren't any leptons because, of course, it's a strong interaction. So I'm going to look at the strangeness here. So the strangeness has to be conserved. So there's nothing strange on this side at all. But all of a sudden, I've got this K on naught, and we have to deduce its strangeness. So this is when we have to look at quark structures. So what I tend to do is when anything to do with strangeness comes involved, I tend to write the quark structures above it. So I know a meson is a quark and an antiquark. This is a pion minus. It has no strange quarks, so it has up and down. And so for somehow I've got to try and make a minus charge. So in this case, this is going to be up, anti-up, down. A proton, of course, is up, up, down. And these two I don't know. So a K on naught has to have no charge and must have some strangeness about it. So it could be, of course, it could be down, anti-strange. It could be strange, anti-down. It could be strange, anti-strange. It could be one of those three. And trying to deduce which one of these is interesting because, of course, I have to try and balance that. So this is a baryon. So all three of these quarks, it's got three quarks because it is a baryon, because it must be to conserve baryon number, have to be normal quarks, if that makes sense. So they have to be non-anti-quarks. So they mustn't have the line above them. So if this one here, for example, looking at the strangeness, this has a strangeness of +1. So its strangeness is +1. The strangeness of this one is -1, and the strangeness of this one is 0. So having a look at what we've got here. So looking at this pion, if we went to a strange anti-strange, that actually implies two things have happened, that both quarks have changed form, which actually would have two interactions. So it can't be this orientation here at all. Okay. So having a look at what this could be. So we've got anti-up, down, and I've got down this one here. Looking at both of these, this is the only one that's had only one change into it. So it's gone from the anti-up to the anti-strange. So what I've got here is I've got this one here, this down anti-strange, is the most likely for this one to be, because for this one to happen, the down would have to change to a strange, and the down up would have had to, anti-up would have to change to an anti-down. That's two interactions to change that. This one is only one interaction's worth of change. Therefore, this is the most likely formation of this K on naught. So this means that the K on naught's structure must be +1, which means to balance strangeness, because it is a strong interaction, this must have a strangeness of 0. So I know that this baryon, so there's 3 quarks, so must have a strangeness of -1, which means there must only be one strange quark, and therefore must also have a charge of 0 as well. So remember, up, down, and strange, this has got a charge of +2/3, -1/3, and -1/3. So this is its charge. They're all baryons, and they've all got a baryon number of a third, and this strange is the only one left. So this here is the answer to this here. So looking at the mark scheme, there are 2 marks awarded, one for realising what the K-on structure was, and one for actually getting up, down, strange. So any 2 of the quark structures correct, then 1 mark. So the fact that I was actually writing these quark structures actually would give me a mark, even if I got this incorrect. So the fact that I've actually written those there, I would get a mark, and for getting up, down, strange would be my 2nd mark. So just to recap how I did this, first of all was I looked at the charge and the baryon and realised it must be a baryon, so it must have 3 quarks. And then I started looking at the strangeness. The strong interaction implies that strangeness is conserved. Therefore, I know that if this has whatever the strange is this one, this must have the opposite. So here, having a look at this situation, this strange anti-strange would imply 2 interactions, because 2 things would have changed, so this one can't be correct. This one here, again, I've gone from anti-up to anti-down and down to strange. This does not feel fluid with what's actually going. Whereas this one, looking at the pion, which was anti-up, down, going to down, anti-strange, actually seems feasible with this interaction. So this is the one I used. So down, anti-strange has a strangeness of +1, which means this has a strangeness of -1. Okay. Another reason why this one is the only one that works is because the only way to get this one here with a strangeness of -1, so if this had a strangeness of -1, this would need a strangeness of +1. I would need an anti-strange quark. And I can't have that because I'm trying to make a straight baryon. Okay, so there's lots of little things that I was doing here, just writing the equations down, writing the information I know actually picked me up a mark. Okay, so the kaon decays by the weak interaction. The interaction is take one feature of the decay shows the weak interaction goes with strangeness is not conserved. If you're ever asked why something strangeness is not conserved, if it's the defining factor of a weak interaction that strangeness is not conserved. You can see that I've got a kaon with strangeness and I've got pions, no strangeness. So strangeness is not conserved. 1 mark. Nice, easy one. Okay. There has been considerable, these questions are always interesting. They're just one of those ones that throw in. There have been considerable advances in our understanding of particle physics over the past 100 years. Explain why it is necessary for many teams of scientists and engineers to collaborate in order for the advances to be made. This is not quite about physics as such. It's more getting your understanding about how science has progressed over the years. So there's 2 marks. So I've got to say 2 things about the situation. Okay, so there are 2 things I need to say about the situation. 2 marks, 2 things. Explain why. So explain, describe what is the point of this. So I'm actually giving evidence why it's important for scientists and engineers to work together. So there are lots of reasons for this. One of them, of course, is the obvious one. With more scientists and engineers collaborate, you can verify data and evidence of experiments by reproducing them in other laboratories. So that one's quite important. Is one of the things about experiments is they need to be reproducible. Okay. And you can verify data and validate anything in here. And if we have a look at the mark scheme here, so experiments must be independently checked and validated, peer reviewed before they're accepted. It can be confirmed. Okay. Another thing, of course, you can say is explain why it's necessary to work to collaborate for these advances to be made. Another thing, of course, is a cost factor. Okay. And again, have a look at the mark scheme on this one. So it's like talking about the cost factors, the cost of building like LHCs and things like that. Talking about many skills and disciplines are required, lots of data to protest. This is the kind of thing they're looking for. So the first one I went for is a very simple one, like you verify data and evidence of experiments by reproducing them in other laboratories. So I'm talking about the fact that you can only verify something is true by reproducing it. And then another one, of course, is saying that by having large numbers of scientists from different backgrounds you are able to design experiments to find information out. So what I'm saying here is that saying that by having lots of different expertise is allows you to design experiments to find information out. If you just had theoretical physicists trying to do an experiment, they don't have the engineering knowledge to actually be able to design and make the LHC. So the whole idea is that there is a lot of this kind of question is a little bit flim-flammy, and it's just basically getting you understanding that for this kind of information, you need to validate your results and that people need to work together. It's the whole point of CERN and any Large Hadron Collider or particle physics thing, is that different backgrounds, engineers, physicists, chemists have all come together to actually make and design an experiment. And you couldn't do that with just one person in a room. To actually make the device that actually is able to produce the data for the physicist to look at is not the physicist, that's the engineer and the chemist working together to be able to get the liquid nitrogen, get the liquid helium down, and etc. So it's one of those things that is really interesting part of physics, that actually how it's all linked together and how they collaborate. It's a bit flimmy-flammy with this question, I won't lie. It's not the nicest question, and I probably would have struggled well in an exam question. But this idea of explain, it's to explain, I'm trying to provide evidence for this fact. So why is it, explain why is it necessary? Well, you verify data and evidence experiments by reproducing them in other laboratories. That is why I'm explaining why you need to actually make these advances. Explain what is necessary. By having large number of scientists from different, you're able to design experiments. I'm explicitly saying you need to design the experiments to find the information out. Okay, so that's what it means to say explain. You are giving details about why something is. Describe is what something is. Describe what interaction. I described what it is. It's very plain. It is this, this, and this. Explain why is I'm trying to give evidence for that reason. Okay. So this is question 1. Hopefully that's given you some insight. This is a very wordy question for particle physics. Hopefully that has given you some insight into that. And stay apart and watch the next video for day 2.